In this recording, we will look at electron configuration for atoms with atomic numbers greater than 18 and the use of something known as the diagonal rule. Start with the electron configuration of potassium. Potassium has an atomic number of 19, and it is in period 4. Period 4 means that we'll need 4 energy levels. So when we start working on this, we always begin as usual at 1s, fill it with 2, 2s, 2, 2p, 6, 3s2, and then comes 3p6. 3p6, at this point we have 18 electrons. We have to consider where do we go next. And in your look at this earlier, some of you went with 3d1, but the correct way is 4s1. So the question is, why does an electron go from 3p to 4s when energy level 3 also has a d sublevel? And the answer to that question is simply the Aufbau principle. It works out that energy level 4s, energy level 4 sublevel s, requires less energy to enter than energy level 3 sublevel d. So the question is, how do you make the decision? Because after 4s, we go to 3d. After 3d, we go to 5s. After 5s, after 3d, we go to 4p. Then after 4p, we go to 5s, and so forth. So it gets mixed up. It's not just going to be fill the first energy level, fill the second, fill the third, fill the fourth. When we get beyond 18 electrons and beyond 3p, we're jumping back and forth between energy levels because there's some overlap in energy levels and the energy required to get into them. So we need a rule. In other words, we need some sort of pattern to follow. That pattern is the diagonal rule. And if you look closely at how this is arranged, you can see we've got all of the s's, 1 through 8, then all the p's, then all the d's, f's, and then g's and h's, and so forth would be out here. The way this is read is we start with 1s. After 1s, we go to the next arrow, to 2s. After 2s, we're going to go to 2p and 3s. After 3s, we go to 3p and 4s. Then after 4s, 3d. So what we end up having is that when we get to the end of an arrow, we go back to the tail of the arrow, next arrow down. So after 2s, we go over to 2p, follow the arrow until we get to 3s. From 3s, we go back up to here, 3s to 3p to 4s. From 4s to 3d, 4p, 5s. From 5s to 4d, 5p, 6s, and so forth. You'll also notice that we go, this particular chart goes all the way to 8s. At this point in history, 7p, if 7p is full, that would represent 118 electrons. So we actually should not have any atoms in ground state that go to 8s or anything out here. So at this point, all of this is currently unused. So let's use the diagonal rule. We'll start with the electron configuration for vanadium. Vanadium has, as usual, we need an atomic number. So Z equals 23. This is also in the 4th period. So that means the maximum value for the energy level, we're going to have at least a 4th energy level. Okay, so we start out with 1s, 2. And we go to 2s, 2s, we go to 2p. 2 electrons in 2s, 6 in 2p. After 2p, we go to 3s. It's 12 electrons so far. After 3s, we go to 3p. That would be 18 electrons. After 3p, we go to 4s. That would be 20 electrons, and from there we're going to go to 3d. And we would have 3 electrons present. You'll notice that we've got a 4s here, so we've got our energy level 4, and we've also finished in the D block. Okay, let's do the electron configuration for germanium. Germanium has 32 electrons. A few things about germanium, where it is located. Germanium is on period 4. So we know we're going to have at least a 4th energy level, and it's also located in the P block. So we're going to finish our electron configuration in the P block. Okay, so we go 1s, 2s, 2p, 3s, 3p. That's 18 electrons at that point. We have to go all the way to 32. 4s comes next. That's 20 electrons. After 4s, come to 3d. So that's 30 electrons at that point. We need 2 more electrons, so we're going to have to go to 4p. And we would put 2 electrons in there. So that would be 30 electrons. 32, excuse me, electrons. Next is tellurium. Tellurium is element number 52. So Z equals 52 electrons. Tellurium is also in period 5. So we're going to have 5 energy levels, and it's in the P block. So that means we would finish with a P electron. So we start with 1s, then 2s, then 2p, 3s, then 3p, then 4s, then 3d, then 4p. I need to put my 10 electrons there, and 4p we're going to have 6 electrons. And that represents 36 electrons so far. So this will represent 36. We need to get a 52. Next comes 5s. Then 4d. So that's 36, 48, 36, 37, 38, 48 at this point. We need to get a 52, so next comes 5p, and that would be 5p4. And that's it. Next, you try. We have the electron configuration for each of the following: cesium, bismuth, nickel, iodine, and lead. Please have these completed when you come to class and in your notes. The next topic is orbital notation. Orbital notation adds to the standard electron configuration by showing orbitals and making use of Hund's rule. You'll remember Hund's rule states that orbitals of equal energy will each have only one electron occupying them before any of them has a second electron occupying. We use blanks or boxes to represent orbitals, and we use arrows to represent electrons. The reason for using arrows is because they are spinning, so we have clockwise and counterclockwise spins, which end up being up spins and down spins when we talk about arrows. So we want to give the orbital notation for oxygen. We begin with the atomic number of oxygen is 8, Z equals 8, and we would do the electron configuration. 1s2, 2s2, 2p6. It's important to remember that orbitals, there are a certain number of orbitals in each energy level. So, for instance, in s sublevels, we have one s orbital. In p sublevels, we have 3 p orbitals. In d sublevels, we have 5 orbitals. In f sublevels, we have 7 f orbitals. So when we have 1s, we're going to draw, I'm going to use blanks. Those are easier to draw than boxes. So we have only one blank representing one orbital. 2s, same scenario, we have one orbital. But in p, we've got 3 orbitals. So we have 1, 2, 3 blanks. We have 8 electrons to complete, and this number is actually wrong. I'm sorry, that should be a P4. So we have 1s2. So we put 2 electrons in this orbital. Notice that we have upspin and downspin. Upspin, downspin, and then 2p. We're going to use Hund's rule, and we say that each of these orbitals is equal in energy. So we have 1, 2, 3, and then we come back and put a 4th electron in with the opposite spin. Okay. This is making use of Hund's rule. Let's try another. We have chlorine. Chlorine has an atomic number equal to 17. So we start with our standard electron configuration. 1s2, 2s2, 2p6, 3s2, 3p5. Electrons in, or actually let's draw orbitals first. S sublevels have 1 orbital, S sublevel 1 orbital, P sublevel 3 orbitals, S 1 orbital, P 3 orbitals. We then draw arrows. 1 up, 1 down, 1 up, 1 down, P6, up, 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 down, down, down. S2, and then P5. 1, 2, 3, 4, and 5. That would be chlorine. We have iron. Iron's going to have an atomic number of 26. So we would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. S, S, P, S, P, drawing the vertical lines just to keep everything separated, S, and then we've got D. D's have 5. 1, 2, 3, 4, 5. S2, S2, P1, 2, 3, 4, 5, 6. S2, P1, 2, 3, 4, 5, 6. S2, 1, up, 1 down, and then D5, we've got up, 2, 3, 4, 5, and then a 6th electron. Now, you try giving the orbital notation for beryllium, fluorine, phosphorus, and scandium. Once again, these should be in your notes. That ends our presentation for this particular video.